Here in chapter 29, we are going to shift gears and take a look at the magnetic field. And we will borrow a lot from what we've learned by studying the electric field, and we'll incorporate that into the magnetic field. There are a few major exceptions or differences, I should say, between the magnetic field and the electric field. We're a little bit more familiar with magnetic effects because as children we play a lot with magnets and compasses. As we can see here, we know that well, if we have played with a magnet before, a bar magnet, there will be an N side and an S side for the north and the south magnetic poles. A needle will point toward close to the geographic north pole of the earth and one to the south pole. That's how we use it for direction. And the part that points towards the north end, the compass needle is a magnetized needle. And the part that points towards the Earth North Pole, we label that the magnetic North Pole. And the part that points to the south, the Earth South Pole, we label that as the magnetic South Pole. Again, if we take just a bar magnet and we put that on a piece of cork and let it float on water, we'll see that the magnet is going to rotate. It'll experience a torque, a magnetic torque due to Earth's magnetic field to align itself with the geographic North Pole and the geographic South Pole. So a magnet inherently has a magnetic dipole. It behaves similar to how we look at the electric dipole. The difference here between magnetism and electrostatics is that for electrostatics, or for the electric field, we can have a single positive charged particle and a single negatively charged particle. We can have what is referred to as an electric monopole, right? We can have a proton, we can have an electron, or we can have a particle with excess proton, we can have a particle with excess electron. Not so for magnetism. Magnetism, the smallest number of poles that we have is a magnetic dipole. At least so far, no magnetic monopole has been discovered. So we can borrow a lot from what we've learned from the electric dipole. Again, a positive charge and a negative charge of the same size separated by some distance d. If you recall, the electric dipole P would have the size of the charge Q times their separation. Let's call that d. Here is plus Q, here is minus Q, and this is distance separation is d. The magnetic dipole moment vector points from the positive to the negatively charged particle. That is your the electric dipole. P, the size of that electric dipole, the size of the vector, is equal to the size of the charge times the displacement. For magnetism, we have a north pole and a south pole and a north pole, and we just described why those are labeled north and the south. And if we put this in an external magnetic field like that of the Earth, it's going to experience a torque, just like if we put this electric dipole, and we looked at this in the earlier chapter, if this is an electric field E, then the electric dipole is going to experience a torque so that it rotates to align with the external electric field E. We have the same thing here for a magnet. If we were to cut this magnet in half, you wouldn't have a single south pole and a single north pole. What we would end up having is two magnets now, right? A south pole and a north pole here, a north pole and a south pole. We would have two bar magnets. So the smallest number of poles for magnetism is a dipole. We can have quadrupole, octupole, we can have any multiple numbers of dipole, but no single magnetic dipole. So that's one major difference between the magnetic field and the electric field. We can visualize or describe the magnetic field of a magnetic material by drawing magnetic field lines similar to how we drew the electric field lines for a charged particle. We had the electric field lines for a electric dipole. If we have plus Q here, minus Q here, we have the electric field starting from the positive, ending on the negative. Again, we put a positive test charge, called this Q test, and the direction of the force that Q test experienced, that would be the direction of the electric field, and therefore any point on the electric field lines tangential to that point would be the electric field vector. So if we put a positive test charge between these two charged particles, this would be the direction in which the object, the Q test, would experience a force away from the positive towards the negative. So this is our electric field lines. And to determine the electric field, then the electric field, say at this point, what is the electric field at this point in space? The vector, the electric field vector, is tangential to the electric field line as that at that point. Okay, so that's what the electric field lines would look like. The magnetic field, since there are no single south pole and no single north pole, and what we don't have the magnetic field line starting at a point, ending at a point. We will always have closed magnetic field loops where it enters the south pole. You can think of this as enters the south pole, leaves the north pole, in complete loop. So it enters the south pole and go through the magnet, right? There's no starting point, there's no stopping point. This is what the magnetic field lines would look like. And we'll get to this in detail in this chapter. Okay, so always closed loop. If we want to determine what is the size of the magnetic field at a point, so at this point, what is the size of the magnetic field? Well, just like electric field, it will be tangential to that point. B is the letter that is normally used, capital B, to denote the magnetic field. This would be the magnetic field vector. If we recall what the electric field, how the electric field was defined, this is the electric force per charge. We will see here for magnetism, this is not going to be the magnetic force per charge, but rather it is dependent on also the velocity of the charged particle. So it's not just the magnetic force per charge, but it is also the magnetic force on the charge. But we have to also take into consideration the motion of the charge. The magnetic field, just the size. So this is not the case. The magnetic field B, or the size of the magnetic field, is not simply the magnetic force per charge, but we also have to take into consideration the velocity. And the velocity we're looking for is the velocity that is perpendicular to the magnetic field. That would be v sine theta, where theta would be the angle between the magnetic field vector and the velocity vector. Again, this is the difference between the electric field and the magnetic field. The electric field is the electric force per charge. The magnetic force, this should have been an E, the electric force per charge. The magnetic field is the magnetic force per charge. So the magnetic field at this point in space on a charge Q is equal to the magnetic force on the charge when it is moving at an angle theta to the magnetic field. And we'll get to this here in a second. The magnetic properties come from the intrinsic property of, say, the electrons and the protons. The electrons and the protons have an intrinsic property that we call electric charge, which happen to be equal and opposite. The magnetic field, as we will see, comes from the inherent property of the electron. The electron seems to be a charged particle that is spinning. We have an electron spin to it, right, which would then generate this this magnetic property. We'll get to that here towards the end of the chapter. A magnetic field is created, or a magnetic field is induced due to the motion of charged particle. In other words, a charged particle plus Q is just simply sitting in space, plus Q will affect the space around it, and therefore we define the effect of that charged particle. How does that charged particle modify its space around it? We define that in terms of the electric field E. and the electric field E is the electric force per charge. So now placing another charged particle at this point will have an effect on the particle due to our plus Q, our source charge here. Let's call it the source charge. Now, having a source charge sitting at rest is not going to alter or modify the space around it at this point R in creating a magnetic field. No, in order to create a magnetic field within that space around it, this charged particle must then be moving with some velocity v. Once a charged particle begins to move, then it modifies the space around it and it creates a magnetic field. The direction of the magnetic field, which we'll get into, is going to be perpendicular to the velocity of the charged particle. We will say again, magnetic fields are always closed loop because there is not a magnetic monopole. We'll see that the movement of a charged particle create these closed loops. So by moving, let's call this the x direction. On the y direction at this point, what is the magnetic field? It would be in that direction. So if this is the x, this is the x direction, this is the y direction, let's call this the z direction. Okay, so then the magnetic field at a point y in space will be in the z direction. Okay, so the charge has to be moving. As soon as the charge stops, there is no longer a magnetic field that's generated. How do we create an electric field? Having a net charge. How do we create a magnetic field? The charge is in motion. It alters the space, creates a magnetic field B. And so that's what we'll get into here in this chapter. So let's look at it a little bit closely. The magnetic field that is created, we can define it in terms of the Biot-Savart law. And it shows us here if we have a charge Q moving, again, let's call this direction the x direction, then this will be the y direction, and this is the z direction. So now magnetism is inherently three-dimensional. Okay, so the object is moving with a velocity in the x direction. This would be v sub x. And let's take a look at a point here, r, away from the particle. Because the object is in motion, it's going to affect the space around it. It is already doing so by creating a electric field. So if we put a particle at this point plus Q, it's going to experience an electric force. But if the charge is in motion, then it also produces a magnetic field. What is that magnetic field at that point? The magnetic field, according to the Biot-Savart law, at that point is going to equal to the size of the charge Q times the velocity at which, or the speed at which the object is moving, the charge is moving, sine of the angle theta. That angle is angle between the velocity vector and the position vector r, divided by r squared. R is the distance from the particle to the point in question. Then we have a constant for the units to work out just right in SI units. It's mu sub 0 over 4 pi, where mu sub 0 is the permeability of free space. And just for comparison, when we look at the electric field from Gauss law, we have the electric field is 1 over 4 pi epsilon sub 0 q over r squared for a point particle. If we have plus q here, as I mentioned, we're looking for the electric field at this point r away. At that point, the electric field is 1 over 4 pi epsilon sub 0. Epsilon sub 0 is the permittivity. That's our permittivity constant. Permittivity, if I can spell that. That's our permittivity of free space. And if my memory serves me right, this is around 8.85 times 10 to the minus 12. And the units there would be coulombs over newtons meters squared. Now in the Biot-Savart law, we have the permeability constant, the permeability of free space. This is mu sub 0, and that is approximately 4 pi times 10 to the minus 7 Tesla meter over amp, or about 1.26 times 10 to the minus 6 Tesla meter per amp, where Tesla is the SI unit for magnetism. So you can see some similarities here, right? The source of the electric field is a net charge. So we have our permittivity constant, and the electric field falls off as 1 over r squared. For magnetism, the source of the magnetic field is a moving charge. The magnetic field, that is due to a charge, but that charge must be moving, and its velocity must have a component that is perpendicular to the position vector. So if we take a look at your velocity vector here, here is your velocity. This is the motion of the charged particle. We're looking for the magnetic field at this point. The blue arrow is our position vector. We can break down the velocity vector as the sum of two perpendicular vectors or vector component. I will draw one such that it is parallel to, let's use a different color here. It is parallel to the position vector. So let's call this V parallel. And then one that is perpendicular, let's call this V perpendicular. And here, that part of that component of the velocity vector V, this is your V sine of theta. And take a look at that velocity vector component. It is perpendicular to the position vector. So the source of the magnetic field at this point P is due to a charge that is moving with a component perpendicular to the velocity vector, so the position vector, sorry. Therefore, if we think about it, if we were looking for the magnetic field at this point on the x-axis, then this becomes our position vector here, which is parallel to the velocity vector. Sine of theta, that's 0. This becomes 0. The magnetic field at this point is 0. So magnetism is inherently three-dimensional. Okay, so to recap, the source of an electric field that we've looked at is a net charge. As long as we have a net charge, there is an electric field. About that charge, the electric field decreases 1 over r squared as you move away from the charged particle. For magnetism, a moving charge affects the space around it. It creates a magnetic field only if it's in motion with a component that is perpendicular to the position vector. In vector form, we can write this as mu sub 0 over pi, that's our permeability constant, times the charge. Charge is responsible, but in order for there to be a magnetic field here, there must be a component of the velocity vector perpendicular to the position vector. And so therefore, the source of, or the direction of the magnetic field can be written as the cross product between the velocity vector and our position vector. Here is our unit position vector r hat. It has a unit of size of just 1. It's a unit vector. It's there to show position. So V cross R, again, the size of that would be V times 1 times sine of theta. So that is V sine of theta. If you recall what the vector cross product is, if we have a vector A and a vector, if this is vector A and this is vector B, and vector C is the cross product between A and B, okay, well, you can use the right hand rule where you use your fingers and you go, again, the order matters here for the cross product. We go from A, take your right hand, you curl your fingers into vector B, and the direction in which your thumb points, that is the direction of vector C. So if I do that with my right hand and I point my fingers in that direction, in order for me to curl my fingers into the vector B, I have to point my fingers down and curl into B, and therefore my thumb would be pointing in that direction. That's the only way I can keep my palms, my fingers extended in the A direction. For me to do that, I have to flip my thumb down to curl into vector B. And therefore, my thumb is pointing down. That is the direction of vector C. This is the right hand curl rule. That's how we can get the direction for the cross product between two vectors. So in this case, the magnetic field vector at this point, how do we get that direction? We will point our fingers in the direction of the velocity vector V, and then we curl our fingers up into the position vector B. For us to do that, I will have to put my hands down on the table, palms up, and then I curl into R. My thumb would be pointing out in that direction. And that's how we get the magnetic field vector. Okay, um, notice the magnetic field vector and position vector here. Those are perpendicular to each other as well. That's a 90-degree there. So the object is moving in the X direction. This is our Y direction. The magnetic field is in the Z direction. The magnetic field vector is going to be perpendicular to velocity. We mentioned this before, the permeability constant is 4 pi times 10 to the minus 7, which is around 1.26 times 10 to the minus 6 Tesla meter per amp. A Tesla is the SI unit for magnetism, and the unit Tesla is a relatively large unit. So a magnetic field of 1 Tesla is a large magnetic field. Just for comparison here, the Earth's magnetic field at the surface of the Earth is about 5 times 10 to the minus 5 Tesla. So that will vary depending on where you are on the Earth. So 10 to the minus 5. So another unit that we would see is Gauss, where if my memory serves me right, 1 Tesla is about 10,000 Gauss. Capital G is used there. The unit Gauss then is used for small magnetic field. So 5 times 10 to the minus 5 Tesla for Earth's magnetic field, that would be roughly about 0.5 Gauss. Okay, so it's a smaller unit that we can use for magnetism. But we're using our equations, we want to use SI units, Tesla, for our units to match up correctly because we're using our permeability constant in units of Tesla. We want our magnetic field to be in Gauss. When we go to get an MRI done, we're looking at those are fairly larger magnetic field. Those are on the order of a Tesla to about 10 Tesla. 10 Tesla would be a very, very large magnet. So since we know that moving charges produces a magnetic field from Bart's-Savart law, we have magnetic field is mu sub 0 over 4 pi. This would be Q the sine of theta over r squared. Now a charge that is moving in a conductor, we refer to that as a current I. So therefore, if we have a current within a wire, there is a magnetic field that is created due to the motion of those charged particles. So in terms of current, we can write the magnetic field induced or created around that wire as mu sub 0 over 4 pi I. Delta S, we're looking at just this little part here of the wire cross R. R is your unit vector over R squared. That would be the magnetic field produced by the current carrying wire. Now, if we take a look at the point here, again, this would be R, and you can imagine now that the magnetic field at this point would be even larger, and the reason why is because the velocity is perpendicular to R. So V sine of theta is now just V, and this would be the direction of the magnetic field. What does it look like for a wire? If we have the current in this direction, okay, we know this would be R. So that's R. This would be V. This is I. The magnetic field B is mu sub 0 over 4 pi I delta S times R, cross R I should say, over R squared. So if we do V curl into R, the magnetic field would be pointing out towards us. Okay, if we do this down here and we do V curl into R, so this becomes R, V curl into R, we use a right hand rule, curl into there, our thumb would be pointing into the board, okay, into the board on this side. So therefore, to represent that, it's kind of hard to draw the vector coming out and vector going in. So we use these dots and crosses. It's like throwing a dart, right? If a dart is coming towards you, all you will see is the tip of the dart. If the dart is going away from you, you see the back end of the dart. And this, this is what the dart would look like. This is the best drawing I can come up with. But if the dart is coming towards you, all you would see is the tip. If it's going away, you would see the tail end to demonstrate that the magnetic field is coming out. And again, because it's closed loop, it loops back in. If I were to draw this with the wire vertical, this current I, at this point, this is R. This is the point we're looking for the magnetic field. This is R. This is the velocity V. So if I do V curl into R, hold my right hand, curl into R, the magnetic field is coming out here and going into the board. So this would be the loop coming out, going into the board. And that would be the direction of the magnetic field lines. And we know the magnetic field is going to decrease as 1 over R squared. So the closer you are to the wire, the stronger the magnetic field is going to be. As you move out, the magnetic field becomes weaker, falls off as 1 over R. Now, if we integrate, okay, along the entire wire, what we end up with for the magnetic field for a straight wire, it's a fairly simple equation. It's mu sub 0 over 2 pi, the current I in the conductor, divided by R. So the magnetic field actually falls off as 1 over R. If we take this current wire and we curl it into a loop, sort of like this, you can imagine this is your loop, and we cut this in half. So what we see here is the current coming out, and then it would loop back and go in. So we're looking at the cross section of the wire. The magnetic field lines that are going to create would be loops like this. These are our loops. At the center of the loop, it's mu sub 0 over 2, I, the current I, times the radius of the loop. Now, if we have more than one loop, then the magnetic field increase by n times. Just to recap, if we're looking now at a top view of the wire, and let's say this is the current direction, that's I, and it's moving this direction. Okay, right at this point, the magnetic field would be going into the board, okay, and coming around here. So going in, coming out. This would be coming out, going in. That would be the direction of the magnetic field. Now, if we put these all together and we create a solenoid, so right here is like having n number of wire at the same radius. But now let's say we begin to stack the coils up. So now that there is a length L to it. The first part here with the loop is like we have n number of loop, but the thickness of the loop remains very small compared to the radius. This is the magnetic field at the center. But let's say now we begin to stack the loop on top of each other, and we have now a solenoid with a current I running through it. We will see towards the center of that solenoid, we have a uniform magnetic field B that's generated. That will equal to a permeability constant mu sub 0, the number of turns or the number of loops that we have to create this solenoid, divided by the length of the solenoid times the current I in that solenoid. the number of turns divided by L, we write that as little n. Okay, so that's a constant value. The magnetic field, whether you're at this point of the solenoid, that point of the solenoid, right there within the solenoid, the magnetic field is constant or uniform inside of the solenoid. Again, to recap, we can determine the magnetic field produced by a current wire. Again, you can use your right hand. You put your thumb in the direction in which the current is moving. Wrap your fingers around the wire. That is the direction of the magnetic field. It's always closed loop because there's not a single north pole. There's not a single south pole. If we were to take this wire and twist it or tilt it in this direction, so this is the current I. Okay, so if you do that, put your thumb in the direction pointing to the left, wrap your hands around the wire. The magnetic field on the top end of the wire would be going into the page and be coming out of the page here. So that's going to be your loop going into the page. If I could sort of do that into the page here, coming out of the page on the bottom, that's going to be your loop into the page, out of the page. Let's take a look at this quicker problem here. We have a long straight wire. So here's the wire we're looking from a top view. So so we cut it. We're looking at top view here. We want to know, is the current going down into the page, or is it coming out knowing the direction of the compass needle? We put these four little mini compass around the wires, and you can see this is the North Pole, this is the South Pole, North Pole, South Pole, North Pole, South, North, and South. The magnetic field line then, what the compass is doing is showing us the direction of the magnetic field lines that this current is producing. And if we sort of connect the dots here, coming out of the North Pole, enters the South Pole, coming out of the North Pole, enters the South Pole, that would be the direction of the magnetic field lines that the current I is creating. So if this is the direction of the magnetic field lines, what is the direction of the current? Well, use your right hand for the magnetic field to be going in this counterclockwise direction. The current must be coming out of this wire. Put your fingers, put your thumb in the direction in which the current is flowing. Wrap your fingers around the wire. That will give us the direction of the magnetic field lines. So this should be coming out of the screen. That's the direction of the current. What about this one? Compare the magnetic field at point A and point B. Well, we know for a straight wire with a constant current I flowing through it, the magnetic field lines will be circular loops. This will be coming out here, going in here. If we use your right hand rule, we can write this as a dot on this side, a cross on this side, right? We're coming out, going in. Those would be the direction of the magnetic field loops. The further you go, we know that the magnetic field decreases. If this is R1, this is R2, the magnetic field for a straight line is mu sub 0 over 2 pi I over R. So as we go out, as R increases, the magnetic field decreases. So if this is 2 centimeters and 4 centimeters, therefore the magnetic field will fall off by, will be twice as small, right? Because we are doubling the distance. We fall off as 1 over R. If we were to draw the magnetic field as a function of distance away, R, from the wire, this would be an inverse relationship, right? This would be a 1 over R relationship here that we have. Okay, so they will fall off by a half, so it would be half as strong, but in the opposite direction. So this is coming out, this is going in. So here, this would be twice as strong as over here when in opposite directions. The magnetic dipole moment of a current carrying loop, remember we talked about the electric dipole moment vector, right? That's from the positive to the negative. For a current loop, so we have the current I, and that is going to produce a magnetic field coming out and looping back in. the magnetic dipole moment vector mu is defined as, or the size of it is the current in the loop times A. The direction would be the direction of the magnetic field that the current loop creates. Okay, so that would be your mu. Recall if you recall the electric dipole moment vector, if this is plus q, this is minus q. Okay, the electric dipole moment vector P goes from minus q to plus q, and the size of that is the charge times the separation. I'll call that d from here to there. For magnetism, then, the magnetic dipole moment vector mu is defined as the current flowing through the loop times the area of the loop, and mu is in the direction of the magnetic field lines there. So if we have a loop, again, the magnetic field lines would be coming out, looping back in, and this is analogous to a tiny bar magnet, right? A tiny bar magnet with a south pole and a north pole. The magnetic field lines enters the south pole, leaves the north pole, enters back in. Always closed loop because then we don't have a single north pole or a single south pole. If we were to cut the magnet in half, what we end up with is a south pole and north pole, and then a south pole and north pole. This would be the direction of the magnetic field lines. Okay, that's what we would have. Always closed loop. So this little loop of current acts as a tiny bar magnet. It's like having a bar magnet here, a south and a north pole. If we then put this in an external magnetic field, let's say we put this in an external field, we have a large magnet here. So we put a large magnet here. This is the north pole. Sorry, that's the south pole. And here is the north pole of the magnet. Then there is going to be an external magnetic field, again, coming out of the north, entering the south pole. That's the external, call this B external to our loop. So what's going to happen to the loop? The loop is going to experience a magnetic torque just as an electric dipole would behave in an external electric field. And that torque is going to cause the magnetic dipole moment vector. So this would be mu. Okay, that is mu. That will cause mu to experience a torque and rotate to align itself with the external magnetic field. So the north pole will line up with the south pole, and the south pole lines up with the external north pole. Unlike poles going to attract each other. What does that mean then? That means for our Earth, here's our geographic north pole, here's our geographic south pole, and if we suspend a compass needle, the compass needle north points to the geographic north, and the compass needle south points to the geographic south. What this tells us is that the Earth itself is a magnet, right? And you can think of within the Earth, there is a magnetic north here and a magnetic south at the geographic north pole. So that an external magnet like a compass needle, its north end is attracted or going to position itself with Earth's magnetic south end. So Earth is one big large bar magnet with the magnetic south pole of the Earth being at the geographic north pole, and the magnetic north pole of the Earth is at the geographic south pole of the Earth. Okay, we saw for electrostatics Gauss law, right, where if we can imagine a Gaussian shell, this hypothetical shell, just by determining the electric flux through that shell, we can determine what is the net charge enclosed by that shell. Our our magnetic equivalent is Ampere's law. Ampere's law tells us that if we go around a closed loop, if we can determine the amount of magnetic field lines that are parallel to that loop, we can determine the amount of current enclosed by that loop. How we write this? We would write this as a line integral where we're looking for the magnetic field that is parallel to our loop. If we cut out a little ds here, tiny length of this loop, this is ds. What is the amount of the magnetic field lines that are parallel to us, hence the dot product, right? Where the dot product, we're looking for the part of the magnetic field that is parallel to ds. And if we do that, we add up all the ds, that's our integral along this closed loop, all the ds. That is going to be equivalent to the current enclosed by the loop times our permeability mu sub 0. So it's sort of analogous to Gauss law, where for Gauss law, instead of a line integral, we were looking at a surface integral, E dot dA, where we were seeking the electric field lines that are parallel to the area vector. And if we add it up across the entire closed surface, that will equal to the charge enclosed divided by our permittivity constant. The magnetic equivalent here would be a line integral. We're looking for the magnetic field lines along a closed loop, and if we've determined what that is indicative of the amount of current enclosed by the loop times our permeability constant. We do that for a solenoid. This is how we can then determine that the magnetic field within the solenoid is constant. It doesn't matter if we're close to the top of the solenoid, the bottom of the solenoid, the middle of the solenoid. It is the magnetic field is uniform inside. That is mu sub 0, little n, which is the number of turns per length times the current flowing through the solenoid. What determines the size of the magnetic field within the solenoid is the current flowing through those coils and the number of coils we have per unit length. And this should remind you of our electric analogy, right? How can we create a uniform electric field? This is a uniform magnetic field. A solenoid produces a uniform magnetic field. How do we create a uniform electric field? We saw this for a parallel plate capacitor or two conductors separated by some distance d apart, where the area of these plates, A, is much, much bigger than the separation D. If we do that, in between the plates, we would have a uniform electric field that is established. If this is plus, this is minus. The electric field in there, E, would be the surface charge density, sigma, over epsilon sub 0. Within the solenoid, this would be the amount of current flowing to the charges times our permeability constant times the number of turns per length. So note here the charge is responsible for electric field. The flow or the motion of charge is responsible here for our magnetic field. So now that we know what's the magnetic field, how a magnetic field is created, what is the magnetic force on the particle? The magnetic force on a particle in a magnetic field, obviously, as we saw before, the particle has to be moving, and the particle has to be moving with a force that is parallel to the electric field. So let's say we have a region where there is a magnetic field B, and it's in this gray plane that we have here, and it's moving. That's the external magnetic field. So you can think of this as having a bar magnet here, and this is the North Pole, this is the South Pole. And we have a charged particle that is moving with a velocity v. What is going to be the magnetic force on that particle? As we mentioned before, there must be a component of that velocity vector that has to be perpendicular to the magnetic field vector. And we do in this case, right? This would be the part of the velocity vector that is perpendicular. That would be v sine of alpha. And once we have that, there is a force. The magnetic force is equal to B v sine of alpha. That is the size of the magnetic force B on the charged particle. Oops, I'm missing the charged particle itself, right? It also depends on the size of the charged particle. So there is going to be a magnetic force on the charged particle if the charged particle is moving and it's moving perpendicular, or at least there's a component of its velocity that is perpendicular to the velocity to the magnetic field vector.
One last thing here about magnetism. We know that current is the source of a magnet, and the electron, the proton, they have a dipole moment vector mu. Again, if you're taking chemistry, right, we use the spin for the electron, right? So the electron is it has this magnetic dipole moment as if though it's spinning, and therefore it's a circular current that's creating this magnetic dipole moment vector. This magnetic dipole moment vector. So even though it's like a point particle, it behaves as though it's spinning like a little tiny current with magnetic dipole moment vector mu. Right, so it has this intrinsic spin, therefore it has these magnetic properties. Now, depending on how the electrons in an atom is oriented, then the net magnetic dipole moment vector is not necessarily zero, and then the element is magnetic, or the material is magnetic. So there are different types of materials. We have um, paramagnetic material, diamagnetic materials, and ferromagnetic materials. So something like iron are ferromagnetic materials, where there are regions. Go to the next slide. There are regions within that iron that are called domains, where the magnetic dipole moments of the iron atoms align. So in this region, here is your net magnetic dipole moment vector mu, and you have all these different regions. Now, when we apply an external magnetic field to the ferromagnets, then the magnetic dipole domain experiences to tend to align with the external magnetic field, making the object then magnetic. If we were to remove that external magnetic field, the alignment remains, and that's how we end up with a permanent magnet. The amount of magnetic dipole moment vectors that we have per volume is known as the magnetism um, um, of the object. Okay. Diamagnetics, just the opposite happens. Whenever we apply an external magnetic field, the domains sort of anti-align, right? So those repel a magnetic field. So if you put those close to a magnet, those are going to um, uh, um, those are going to repel a magnet. Okay. So I misspoke there. The magnetic dipole moment per volume is not the magnetism, but the magnetization is the word I wanted to use. That's the amount of the size of the magnetic dipole moment per unit volume. Then there are uh, um, a special type of material. These are superconductors, right? Where once you get to a certain temperature, the resistance will go to zero, and those seem to expel. They become perfect diamagnets, where they expel external magnetic field. There are some regions within the superconductors where the magnetic field do tend to penetrate and sort of pin the ferromagnet in place. And you may have seen these before, these magnetic levitation, where you have a semiconducting material that is hovering on top of a permanent magnet, right? That superconducting material is behaving like a perfect diamagnet. It is repelled from the magnet, but it's held in place because some magnetic field is able to pass through or pin the object in place. If we were in class, I would have. We do have a setup, but this is a magnetic track, and on top these pucks are made of a superconducting material. So whenever we cool it down, in this case I use liquid nitrogen to cool it down, it becomes superconducting. And now if I play the video, you can see the magnets just hovering on top of the permanent magnets, but they're pinned in place there. So most of the field are repelled, some are able to get through, and therefore the magnets are held in position. Even the ones on the bottom there, you can see that small puck on the bottom is sort of floating there in the air until the puck cools down. Those would then lose its property and fall